Hey there, my fellow intellectuals. A few days ago, I was looking through a textbook of mine, and I saw the following integral. And I couldn't help but feel deja vu because I was like, where have I seen this before? And if you look at this result, this root pi, you might know that I have a video on my channel that has an integral with the same exact result, which is the Gaussian integral. So the Gaussian integral is e to the negative x squared dx from negative infinity to positive infinity. And that also has, root pi as its answer. And so when I saw these two results, I couldn't help but think, is this integral, is that just a disguised form of the Gaussian integral? And sure enough, yes, it is. And since I've already done a video on the Gaussian integral, I won't go into the nitty-gritty details of how to solve it because I've already dedicated a whole video to it, but I will show sort of unveiling the disguise of this integral as the Gaussian integral. So to start, let's just go ahead and start with the integral given. So 0 to 1 du over square root log 1 divided by u. And the first thing that we want to do here is we're going to make a substitution. We're going to let a new variable t equal the thing underneath the square root, log of 1 over u. And if we take the derivative of t with respect to u, we have to apply the chain rule here. The first part is the outer part, so we know that if you take the derivative of log x, you just get 1 divided by x. So in this case, we'll have 1 divided by 1 over u, which is just u. And then we have to multiply it by the derivative of the inside, which is 1 divided by u. And the derivative of 1 divided by u, this is just negative 1 over u squared. I said this is just u. So we'll have dt du. Oh, that was a weird u. I don't know why I wrote that there. That's just equal to negative 1 divided by u. And so if we solve for the differential du in terms of t, we'll get dt is equal to negative du over u, or negative u dt is equal to du. So we need to rewrite this u in terms of t, which we can do using this line up here. So what we can do is that we can exponentiate the thing I just circled. So we can say that e raised to the t power, right? And then we raise the right-hand side, which is this log 1 over u. But if you take, e to the log 1 over u, this exponential and this logarithm cancel each other, so we just get 1 over u. So essentially, 1 divided by e to the t is equal to u. And we can write 1 over e to the t, you can just rewrite that as e to the negative t. So in all, we can have that this line up here is negative e to the negative t dt is equal to du. And so what we can do now is we can look to rewrite this integral, but we also need to consider what the bounds are, right? These integration bounds are in terms of u, but we want them in terms of t. So let's think about the relationship we just established here. What we're going to do is we are going to use this, or actually I think we could use this relation right here. So let's just say e to the t is equal to 1 over u. So if u is equal to 0, 1 over u is infinity, so that means e to the t equals infinity, or t has to be infinity. Now if u is equal to 1, then we have e to the t is equal to 1, which means t has to be 0. So let's put that back into the integral here. So rewriting this integral now, we have integral. Now the lower bound is going to be infinity because that corresponded to u equals 0, and then the upper bound is going to be 0, which corresponded to u equals 1. And now we have to rewrite the top part, which was du, and we found that du is this e to the minus t dt. I'm just going to go ahead and copy this and bring it down here. Okay, e to the minus t dt, and then we have to divide this by the square root of log of, remember we had log of 1 over u in the denominator, but 1 over u we found is, it is here, sorry, I was like, couldn't find it right here. So it's e to the t. So we have log e to the t. Which is nice because log of an exponential is just the thing and the exponential's argument, so we can have infinity to 0, negative e to the minus t dt, then we'll have square root of t. And now we're really close to the, recreating or unveiling the disguise of the Gaussian integral. Essentially, if you don't like this infinity to 0 bounds and you want to flip them, we can introduce another minus sign at the to flip those bounds. So I'm just going to do that again, or not again, but I'm just going to do that. Minus t dt over root t. And now these two minus signs are going to give me a plus sign. So we currently have 0 to infinity e to the minus t dt over the square root of t. And now we're going to make one more substitution. We're going to let x equals root t, right? And so we take dx dt. We're going to get, well, remember root t is just t to the 1/2, so this should be 1/2 t to the minus 1/2, which just equals 1 over 2 root t. So we'll find that dx is equal to dt over 2 root t, or we'll find that 2 times dx is equal to dt over root t. Now I wrote it like this because if you notice, I'll use a different color here to illustrate it, we have this dt over root t right there, so we know how to express that in terms of x now. And thankfully, because of the integration bounds, because x is equal to root t, the integration bounds are going to stay exactly the same, as in if t is equal to 0, x is equal to 0. If t is equal to infinity, x still equals infinity. So we're going to have 0 to infinity. Now we're going to have e to the minus, now if x is equal to root t, that means x squared is equal to t. And now this dt over root t can get replaced by 2 dx. So essentially we have 2 times 0 to infinity e to the minus x squared dx. This is awfully familiar now. The only thing we need to recognize, and that is a really terrible infinity, so I'm going to redraw that. But essentially is that since e to the minus x squared is an even function, and we know that to go from 0 to infinity is just the same as, or going 2 times from 0 to infinity is just the same as going 1 time from negative infinity to positive infinity. So essentially we're just going to go over the entire x-axis here, and we get e to the minus x squared dx, which of course, as you know from above, this is our Gaussian integral that I was saying that was disguised this whole time, and so we know that the answer to this is root pi. So I hope you enjoyed this video. I hope you enjoyed watching the disguise get unveiled, and I hope you will tune in next time for more math videos like this. So thank you for watching.